I don't have any kind of like lesson plan like written out. I just am winging it because that's how I do things. I've been working on prime numbers. I'm working through my math books and everything, and I'm starting back at the beginning. And so I came across prime numbers, and once I find something that I can't explain easily myself, I have to delve into it. So it's like, you know, decimals and fractions. That's fine. I know how those work. But I came across prime numbers, and I came across how to find a prime. And this damn book, Basic Mathematics for College Students, okay? Don't ask why, I just have this book. I don't know why I have it, but I do. Don't know where it came from. And so I'm starting at the beginning. I'm in chapter 2, and I'm in prime numbers. You know, it's just a fucking textbook. And this is the problem with math and the way that they teach math, is because prime means if a number has exactly 2 factors. So prime is just a characteristic of a number. When you start getting to know numbers, like getting to know them, prime is just a characteristic. Just like if a number is even or odd, or if it's irrational, those are just characteristics of numbers. So prime numbers are just a characteristic of a number. So when you run across something like a 13, you just know that that's a prime number. It's got exactly 2 different factors, i.e. 23 is 2 factors, 1 and 23. Yeah. 12, you can't really see it. 12 is not prime, it's composite. Prime or composite. 12 is a composite number because it has more than 2 different factors. It's got 1 and 12, 2 and 6, and 3 and 4. So I'm learning about the Sieve of Eratosthenes. And with the sieve, you can put any number through the sieve to find out if it's prime or not. And I understand the visual representation of the sieve, but this has this other... To determine whether a number is prime, so if you just give me any random number, you can put it through the sieve. And there's one way of doing the sieve, and it's drawn out. It looks like this. Okay. So it's got it like visually represented on like a graph. I don't know what you'd call that. It's like a graph where you have 1 through 10, and then you can mark out the numbers that are multiples of primes, basically. And you can do it visually that way, but that's going to take a long time. And so there's a mathematical way of finding if a number is prime. And this book tells you how to do the mathematical way, but it doesn't explain why the mathematical way works. The book will explain how if you're testing if a number is prime, so like 173, we're going to see if that's prime or not, that you're going to divide it by its prime numbers. And so I understand, I'm not really going into this. First you test if it's divisible. 173. Is 173 divisible by 2? No, because it's not even. Is 173 divisible by 3? Well, you can easily check if something's divisible by 3. You add the numbers, and if those numbers are divisible by 3, then it's divisible by 3. An example is 27. The number 27, is that divisible by 3? Well, 2 plus 7 equals 9. 9 is divisible by 3, so yes, 27 is divisible by 3. And that accounts for 6s and 9s as well. So you can test if something is divisible by a 3 or 6 or a 9 just by adding the numbers. And if it comes out to a divisible by of 3, then you can know that it's divisible by 3. So like 157. 1 plus 5 plus 7 is 13. plus 3 is 4. So no, 157 is not divisible by 3. You can just do that. So we're looking at 173. Is it divisible by 2? No, because it's not even. Is it divisible by 3? No, because 4 plus 3 is 7, and 7 is not divisible by 3. And then 1 plus 7 plus 3, is 8 plus 3 is 11. Anyway, yes, it's not divisible by 3. And is it divisible by 5? No, because it's not a 5 or a 0. So you can just test 2, 3, and 5 real quick. But from there, you have to go up, and you have to just test about the other multiples of the other prime numbers. So the book explains that as you go up, you divide by other prime numbers until you find a prime number that the quotient is smaller than the divisor. So like in 173 divided by 7, the quotient is 24, remainder 5. 24 is larger than 7. So we move on to the next one, to 11. 173 divided by 11, the next prime number up, is 15, remainder 8, and 15 is larger than 11. The quotient is larger than the divisor. And so you go up to the next one. 173 divided by 13. Well, 13, I'm not going to get into it, but this 13 is not smaller than this one. They're the same number. So you go up to the next one. Now 173 divided by 17. 10 is smaller than 17. So the book tells you that you stop once you reach a quotient that is smaller than the divisor. So it gives you this mathematical formula, because I can keep going. 173 divided by 19, your next prime number is 9 over 19. 9, the quotient is larger than 19, the divisor. And then you can go up to 23 and 29, but I didn't, because that quotient is just going to get smaller and smaller to 1. I didn't just do this with 73, I did this with a lot of primes. But the book doesn't explain why you stop once the quotient is smaller than the divisor. The book doesn't explain that. And so, this is just me from last night. I'm testing composites. Is 323 divided by, is it prime? Well, it's divisible by 17. 221, it's divisible by 13. 223 is prime. Okay, well, find the largest factor lower than the number. Everything above is irrelevant, right? Y'all can't see this, but this just goes. Yeah. My whole board is full. My whole board is full because I was working on this last night. Because that's the thing. It's I have to understand it well enough to explain it. Other than I don't understand it well enough if I can't explain it simply in simple terms. So I was trying to figure out why the hell that equation that the book, or that system, I don't know what the right name for it is, why that works. Why do I stop testing prime numbers as soon as that quotient is smaller than the divisor? I don't know why, but the book says to stop after that. But fucking why do you stop after that? Couldn't there still be a possibility that there's more prime numbers? If I'm testing if 173 is a prime number or not, why do I stop? There's still other numbers it could be divisible by, so why the hell do I stop? Well, I found out. So I'm going to break this into addition. So decomposing numbers, right? I did a video on that. Every number can be broken up. So let's do 10. Okay. When you break up 10 into its counterparts, 10 plus 0 is equal to 10. 9 plus 1 is equal to 10. 8 plus 2 is equal to 10. 7 plus 3 is equal to 10. 6 plus 4 is equal to 10. And 5 plus 5 is equal to 10. Now, right here in the middle is a turning point. It's the halfway point. Because once you hit 5 plus 5 is equal to 10, you see how the number on the left is going down and the number on the right is going up, right? 10 goes down to 5, and then 0 goes up to 5. So after you hit this halfway point, they're just going to mirror each other. So we started at 10 on the left and we went down to 5, and now after 5 you're going to go down to 0. But you see, like, if we keep going this direction, if we keep going down, we're going to hit 3 plus 7, but 3 plus 7 has already been satisfied. So anything above the halfway point is just going to repeat itself. It's already been satisfied. So like, we can keep on going up to 1 plus 9 down here. But we already know 1 plus 9 is 10 because we dealt with 9 plus 1 up here. So you have this halfway point that if you keep going beyond that halfway point, the partner, like 9 plus 1, 1 is 9's partner to get you to 10. Well, you can go all the way down to 1 over here, but 9 plus 1, they're partners. You've already satisfied 9 plus 1, it's up here. So you only have to go halfway. And anything after the halfway point, the other number, the partner, the other part, is going to have already been satisfied from above the halfway point. So it works the same with multiplication, with factors and multiples. So with like 100, 1 times 100, 2 times 50, 4 times 25, 5 times 20, and 10 times 10. Okay. This is where we stop listing the multiples or the factors of 100, because we can keep on going. This number can keep going up, but we're just going to repeat this side. So what happens? We go up to 20 times 5. We go up to 25 times 4. We go up to 50 times 2, and we go up to 100 times 1. So once you hit the halfway point, if you keep on going up, all you're doing is satisfying things that have already been satisfied. 20 times 5 has already been satisfied with 5 times 20. So once you hit that halfway point, you can just stop because you've already done both sides. You've already done the small number and the large number. Because as this number keeps getting larger, it's just going to start repeating itself mirrored. 20 times 5 is 5 times 20. 25 times 4 is 4 times 25. Like, we don't have to keep on listing the multiple or the factors after we hit the halfway point. Well, what's the halfway point when it comes to multiplication? It's the square root. Because the square root of 100 is 10. The square root of 100 is 10. So 10 is our halfway point. What number times itself is going to get you to that number? Because as soon as you go larger than 10, then its partner is already been satisfied. So once you go over the square root of a number that you're trying to find the prime of, then you don't need to keep on testing. So the square root, drop my phone. The square root of 173 is 13.5. 13.15. Okay. Square root of 173 is 13.15. So when you're looking at factors of 173 to see if there are more than 2 different factors or not, you test 173 for 2, you test it for, it's not divisible by 2, it's not divisible by 3, it's not divisible by 5, it's not divisible by 7, it's not divisible by 11, it's not divisible by 13. But once you get to 17, you know to stop, because since the square root of 173 is 13.15, this is the halfway point. $13.15 is the halfway point. Just like with the addition, 5 plus 5 is a halfway point to 10. Just like multiplication, 10 times 10 is the halfway point of 100. So 13.15 is the halfway point of 173. So that's why when we divided 173 by 13, our answer was 13 remainder 4. Alright, well, that's inconclusive. We need to test the next prime number above. Well, because once you reach a prime number that you're dividing 173 by, and the quotient is smaller than the divisor, you know that you've gone beyond the halfway point of the square root of this number. And once you've gone beyond the halfway point, as we can see here, anything beyond the halfway point has already been satisfied here. So once you go beyond the halfway point of the factors of 173, anything larger than 13.5 will have already been satisfied by everything smaller than 13.15. That's why what the book tells me, why it works the way it does. Because you're looking for the factors of. So I guess I can try to break this down in one that's a little bit easier. Let's do 12. Alright. What's the square root of 12? So with multiplication, you're dealing with roots because it's whatever number times itself. Just like whatever number adds by itself. Over here, 5 plus 5 adds to itself to get us to 10. But here we do 10 times 10. What number times itself will get us to the number we're looking at. So the square root of 12 is 3.464. So when we're testing the factors of 12, 1 times 12, 2 times 6, 3 times 4. Okay. This number, the left-hand side, keeps getting bigger. 1, 2, 3. The right-hand side keeps getting smaller. 12, 6, 4. Okay? They're inversely proportional. So you start with 1 and 12. 0. 1 and 12. Right? If you think about it that way. Well, then you've got 2 and this goes up to 2. This goes down to 6. I know I built on that one, I didn't build on that one, whatever. So at 1 and 12, then you've got 2 and 6, and then you're going to have 3 and 4. Okay, you see how this one goes up and this one comes down. So this number is going up, it's getting larger, and this number is going down, it's getting smaller. And that's going to happen until you hit 3.464. Okay. Because at 3.464, they're just going to flip on each other. Yeah, because 3.464 times 3.464 is equal to 12. So we don't need to go above 1, 2, 3. We don't need to go to 4 on the left-hand side because 4 is already satisfied on our right-hand side. Anything above 3.464 is going to be already satisfied in this column. So once we hit a number that is smaller than the square of itself, because 13 times 13, the square is still smaller than 173. The 13 times 13 is 171, I think. 169. Maybe 169. Yep, I was right. 169. 13 times 13 is 169, which is still smaller than 173. So we're on our factor tree of 173. 13, the prime number 13, is still smaller than the square root of 173. So you're still on the small side. And then once you go above 13.15, then everything else is going to have already been satisfied. So you don't need to test any further than the square of the number. If there are no factors on the lower side of the square of the number, then it's prime. That's why the sieve. Holy shit, this is 27 minutes. Damn, okay. That's why the Sieve of Eratosthenes works. Fuck the book. Math, they'll just tell you, oh, put it into this formula. Why the hell does that formula work? This is why. This is why the formula works. I was at this for a few hours last night trying to figure out why it works, but this is why it works.